Alright, let's get started. Last day of new material. Final syllabus time, it's what, like 11 o'clock on Monday or something, the 11th? Or 10:30? What time? Alright, 10:30. It's in the syllabus. It should be in GMCS 333. It should be in GMCS 333, it's in the same room the first and third exams were in. Next week will be review. Even though we don't have class on Friday, I'll hold office hours from 9:30 till 12. So my normal office hours plus more classes. So at the end of class on Wednesday, I talked about the Gabriel synthesis as another way to make amines. I will still go on record to say the azide route followed by hydrogenation of the azide is still, in my opinion, the way I would go. But this is the classic amine synthesis. And so you start off with phthalimide. Phthalimide is an amide, but it's actually an imide in that instead of having one carbonyl adjacent to it, it's got two carbonyls. So as you would expect, phthalimide or an imide is going to be more acidic than an amide because it has two carbonyls rather than one, so it has twice as much resonance. So for the same reason that a dicarbonyl compound is more acidic than a monocarbonyl when it comes to enolates, because there's more resonance. And so KOH will more or less irreversibly deprotonate this, giving us our phthalimide anion, which will then attack an alkyl halide, an SN2, which is a common theme for amine synthesis, giving us this guy right here, which is the phthalimide, the alkylated phthalimide. And then what we typically do then is we then throw in hydrazine, rocket fuel, and heat the bejesus out of it. And what we get out will be our amine, our primary amine, and this can only give primary amines, plus this byproduct. And so I showed you this last semester, last Wednesday. Now it's time for me to kind of show you the mechanism. And I said it's a bunch of acyl transfers. That's all it really is. And so hydrazine, first and foremost, it's an amine, right? And when we heat the heck out of it, it can most definitely add into one of these carbonyls, giving us a tetrahedral intermediate, which will collapse and then do a proton transfer to give us this ring-opened, amine. So it adds proton transfer, opens up the ring. So it adds in tetrahedral intermediate. Tetrahedral intermediate kicks out this group as an amide, followed by a quick proton transfer to grab the proton. Then that'll give us this bis amide ring opened product. And now we get to this next step, which explains why we need hydrazine. And we just can't do this with a normal amine. So if we look at this with the hydrazine, the first nitrogen is bound to a carbonyl, so it's going to have amide-like reactivity. What about the second nitrogen? Is the second nitrogen going to act like an amine or an amide? It's going to act like an amine, right? Because it's not bound directly to the carbonyl. So this is why we need hydrazine, is because with hydrazine, we have the second amine, which can do the second nucleophilic acyl substitution step. Whereas if we just used ammonia, we would be stuck with the ring opening. So because we have the second amine can now add in, giving us a tetrahedral intermediate, which will then eventually, well, let me draw the tetrahedral intermediate because you guys like to see them, which is good. So the second amine is going to add in. It's going to give us a tetrahedral intermediate like this. The amine is then, this amine in orange is going to grab the proton from this. I'm just, because lack of room, I'm just going to draw the product up. And then this minus charge on mean takes this proton to give us this species. So again, I just drew a proton transfer. And then what's going to happen is that it will eventually kick out the mean. It will kick out the ammonium, to give the product. Sorry, I missed the proton on my steps. But anyway, it will give this with an NH here, it will add here, and then we'll have a proton transfer where one of these protons goes to the amine, gives us an ammonium, and then it kicks out the ammonium to give us our amine as a product plus the guide. I'll be honest, mechanistically speaking, this will be the Gabriel synthesis is a predicted product type of question in my opinion. There's more interesting mechanisms to ask. But the key thing to remember is you do need the hydrazine in order to cleave the hydrazine to give us our primary amine. And the hydrazine adds in, there's one nucleophilic acyl substitution, and then the second amine adds in, and there's a second nucleophilic aromatic substitution, which upon a proton transfer kicks out our amine as a product. Yes?
That step right under the heat, why doesn't the the hydrazine kick off like the swearing?
Well, it's like the swerm. There's not
Oh, there's like the CL kicks off in the swearing. I'm just curious why the nitrogen and nitrogen.
Well, it's equal. It's all equilibrium, right? Oh wait. Are you saying why the other nitrogen doesn't kick off, or if you had a positive? I don't want to say it doesn't. Well, in this situation, it will not happen. And there's no reason for it to happen. I'm going to show you a situation today where the nitrogen-nitrogen bond may break, but for that, there's really, really strong reasons why. And it's different, but if I say it doesn't, and then I go into chemistry and talk about it, it'll confuse people even though it's completely different. So I'm carefully choosing my words. There's no reason, there's no electron pushing way you can draw that would be reasonable for one of these amines to leave. You could not draw an electron pushing way that would be reasonable. And that's the reason why it doesn't leave. If you could draw an electron pushing way, then it could. But in this case, I dare you to try. You won't be able to find a reasonable way to push electrons for it to leave. What I thought you were asking is why doesn't, in this step, why does this leave instead of the hydrazine? Why doesn't the hydrazine leave? And the answer is, it's a nucleophilic acyl substitution. It's all equilibrium. You know the hydrazine does indeed leave at some point, but then just adds back in, and eventually the equilibrium is going to favor the product because it gives you, two stable things, and so that pushes the equilibrium forward. But the key thing, you need the hydrazine in it. And if you can't tell by my enthusiasm towards this reaction, the big thing to remember is deprotonated element, SN2, hydrazine cleaves it to this type of mechanism to give us our primary amine act. Since I have called the shots for my research on my students, anyone who's ever had to make an amine, I say, here's some sodium azide. Go the sodium azide in. So remember from yesterday, the sodium azide route. The sodium azide route was again still an alkyl bromide or an alkyl halide plus sodium azide. Still does an SN2 reaction. Now give us an alkyl azide. And then instead of heating the heck out of it with rocket fuel, you take palladium and carbon, an H2, and it'll give you your amine out. So this is the way a boss will do it. The one thing, since I have the azide drawn up just for fun, let me draw the resonance of the azide, because I think this will also give you guys some more insights into how an azide kind of can react. So here's the one of the resonance structures of the azide. And you see you have N2 right here. So, you know, really strong leaving group. And you can see that this nitrogen has a minus charge in this resonance structure. Which means in this azide resonance, this nitrogen still has a nice partial minus charge. And so it's pretty much the palladium kind of inserting between these two bonds and hydrogenating it off. We know palladium is Lewis acidic, so when we talked about the palladium catalyzed hydrogenation of alkenes in 232, we talked about the palladium would actually coordinate to the pi electrons in the double bond. And so we know palladium likes electrons. And so the same idea is this will probably kind of glob onto the palladium and cause the chemistry to happen. Don't worry about the mechanism. I just felt like drawing the azide resonance structure. Give you guys a chance to kind of see kind of what an azide might look like in reality. So in my notes after Gabriel, I talked about reductive abominations, but of course I talked about reductive abominations a lot last time, so I kind of did it partially in order. But just to remind you guys, the basic idea of a reductive abomination is taking your primary amine, taking your aldehyde or ketone, and then taking your amine. So in this case, let's just draw a primary amine. But of course, we can use any amine as long as it's not a tertiary amine. And of course, maybe a little bit of catalytic H3O. And what are we going to form with a primary amine and an aldehyde under catalytic H3O? The amine. A mechanism you guys should be well familiar with by now. So then you get your imine, and then once you have your imine, then you add in sodium borohydride. And then the mechanism for all intents and purposes is under catalytic H3O conditions, there will be some of this product that will be protonated. So it's just the H minus adding into the carbonyl. To give us our amine. Just the color coded a little bit better. H3O. So the hydrogen on the carbon comes from the sodium borohydride, and then the hydrogen in the amine just comes from whatever acid you used. So again, I talked a lot more about this on Wednesday, but just a quick review for reductive amination. You pretty much go through the amine and reduce the amine, usually using sodium borohydride. Why would using lithium aluminum hydride perhaps not be a very good idea? It's obviously a strong enough reducing agent, so we can obviously do the reduction. But under typical conditions, with a primary amine, why might we try to avoid lithium aluminum hydride? Well, the big thing is that it's very, very basic, right? And so a lot of times what people like to do is they'll take the aldehyde, the amine, and the sodium borohydride and just dump them together at once and then let it stir and come back. That's actually what people really do. They add all the reagents together and walk away. Mechanistically, I show it to the amine because I wanted to point out it goes to the amine. But in general, you dump everything together and you walk away a lot of times. And so what would happen with really, really basic lithium aluminum hydride and stuff like calic acid and amines?
You have a pretty big reaction.
Yeah, exactly, right? Lithium aluminum hydride spontaneously combusts, well, it's not spontaneous, but it combusts in the presence of water. Or H3O, or even, base, amines, which are still somewhat acidic and still react. So, you could, in theory, do it if you preform the amine, purify the amine, and add it in lithium aluminum hydride, for sure. But, why would you use a sledgehammer when you use a chisel? So, sodium borohydride is a good one. In reality, sodium borohydride works great. But what chemists really like to use are borohydride reagents that only have one hydride. So, let's give you an example of one. So, it's sodium trisacetoxy borohydride. So instead of having 4 hydrogens, it has 3 acetoxy groups. Do you think this will react similarly to sodium borohydride, more or less? Yeah, it would. There's not that big of a difference. It's a boron with a hydrogen. It has a minus charge. So this will react. People usually use borohydrides with 1 hydride instead of ones with 4 hydrides, just because it gives you more control. So this is sodium trisacetoxy borohydride. Its acronym that everyone uses is sodium tris acetoxy borohydride. So I have known people who have set this reaction up, and as they add the trisacetoxy sodium borohydride, will go stab, 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 and then I would know they were doing reductive amination. But for all intents and purposes, sodium borohydride is fine. I just wanted to say stab, stab, stab. And now you guys will remember, anyone who decides to be a chemistry major, that if you really do a reductive elimination, you might consider using a borohydride with 1 hydrogen. So, on the arc of fun things to say, the last concept we'll be talking about is the reaction of amines with sodium nitrate, NaNO2, and H3O conditions. And just to draw you guys the product out before I get into the mechanism, the product that we'll get out will be what we call a diazonium species. Yeah?
Is it nitrite or nitrate? You said nitrate, you drew nitrite.
I've never taught Chem 100. It's NaNO2. And there's a reason why I shouldn't teach Chem 100 or Chem 200. Because 8 and 8 I always confuse. It's sodium NaNO2, so never organic kind of stuff. So NaNO2 and H3O. So under these conditions, so let me draw out whatever it is, NaNO2. So under acidic conditions, this forms a reagent that's So this minus charge of the oxygen can be protonated by the oxygen, and it gives us HONO, something that organic chemists lovingly call, does anyone want to guess what we call this?
Oh, no.
HONO. And has anyone seen Game of Thrones? There's a character from Winterfell who has this catchphrase. And so I started calling it, for some reason, I always just call this HONO. HONO, just so you don't forget it. So my students for 432 last semester joined my lab. I had one of them do one of these reactions, and the entire time they were going, HONO. And I know I did my job right. So, I mean, you can't forget, part of my job is to teach you something so you guys remember it, right? So it's pretty hard to forget me saying, HONO. So, sodium NaNO2 and H3O will give us this reagent called HONO. All right? And then HONO will react with amines to give us reagents like this that we call diazoniums. So just to go through the chemistry, and let me just tell you, the chemistry is not that different than chemistry we talked about of amines adding into carbonyls. Instead of the carbon-oxygen double bond, now we're talking about the nitrogen-oxygen double bond. So we form HONO, and we're still under H3O conditions. Do you think there's anything else that can happen? Well, so this is still an sp2 amine that has two very nice electronegative groups next to it. What actually happens is, well, and that can happen a little bit, but this is also a protected pathway idea. Once from HONO, if we were to, in theory, protonate this alcohol again, which we do to some degree, it can just leave. To give us a nitrogen double bonded to an oxygen with a positive charge of a nitrogen. So this will spontaneously form, giving off water. And the formation of water is the driving force to form. I guess if this is HONO, I guess this will just be no. And no big surprise, since there's a positive charge of the nitrogen, it's very electrophilic. And so your nitrogen will attack it. And that's the only arrow you have to draw because it's a positive charge that wants electrons. So it's just going to take those 2 electrons from the nitrogen. There's no electron flow other than that. Yes?
Shouldn't it be a minus charge?
No, because it's giving its electrons to water. So the positive charge on the H2O plus N, these 2 electrons go to water, so water will be neutral. And the positive charge from the oxygen can be transferred to the nitrogen.
Okay.
So that will attack. It will give us a species like this where now this nitrogen has a positive charge. Then we'll have something that's almost reminiscent of a tautomerization. I'll draw it stepwise. Where this will grab this proton from the amine. And then these electrons will go into this nitrogen, causing these electrons to go and quench the negative charge of the oxygen. molecule. So once again, all of this stuff here, you could just draw as its taumerization. Do you see why I'm saying calling this a taumerization? Yeah, yeah, exactly. This is very similar to taumerization.
Should there also be a hydrogen element?
Yes, you are right. And then we'll do a second detaumerization now, where then this nitrogen now has a positive charge after we did. It still has a positive charge after the full detaumerization. So now this will grab this proton. Really, I didn't need as much board space as I thought I did. So then this oxygen takes this proton again, and then we can just draw a reaction where we kick off, these number of electrons go in, to kick off the water. Give us our diazonium. So once again, it's NaNO2 under H3O conditions, it gets protonated once, gets protonated a second time, water kicks off, and it gives us NO+. So honochemistry will eventually form under acidic conditions NO+. All right, so NO+, or NO, will then be attacked by the nitrogen to give us a compound like this. Then low pair of electrons on the oxygen and the nitrogen grab a proton, have a positive charge, then low pairs of electrons and nitrogen kick in the almost to an enolate type mechanism to quench this minus charge, give us a compound like this, still with the hydrogen and the positive charge and nitrogen, and then this OH can again take this proton, give us water, which just leaves, and then these low pair of electrons go in, kicking off the water to give us our aryl diazonium. So the mechanism itself is not too crazy. It's basically just an attack of an NO plus followed by a double taumerization. Or another way to think of it, instead of using the T word taumerization, you could just say proton transfer, proton transfer, proton transfer. To go from honochemistry, and let me kind of circle this stuff as a almost separate mechanism in its own right. Selenium nitrite under H3O conditions to get NO+, and then it being attacked and having a couple electron transfers, as well as a number of electrons donating into stuff, which is why we call it a taumerization, to give us our aryl diazonium. Yeah?
So taumerization, is that synonymous with intermolecular proton transfer? Intramolecular proton transfer?
I wouldn't say synonymous. If you look at the end result, it does look like an intermolecular proton transfer. But again, when you look at the nitty-gritty, it could be intermolecular or it could be intermolecular. But again, the general thought people say is intramolecular proton transfers will work most of the time. Inter will work all of the time. This is a good mechanism just to be familiar with. It looks kind of crazy at first, but it's not that bad. Just it's proton transfers and electrons going into high star orbitals. Think of it this way: it's proton transfers and resonance. So, the thing about diazonium compounds, does this to you look like a very stable compound? Absolutely not, right? It will give up N2 and explode at the bat of an eye at most temperatures, yeah.
How come the positive charges are just on the nitrogen and the water leaves on its own, the other nitrogen?
You can draw it that way.
So that would be like the same thing.
Yeah, so I drew this as an E2 type mechanism. What you proposed was an E1 type mechanism. And in this case, I think you could draw both. And, the E1 might even be a little bit more reasonable. But just the way my mind works, I look at this as an E2, but what you propose is perfectly fine. So yes, these diazoniums, like these, are not stable. So if you just have an sp3 carbon adjacent to it, they are not stable even at minus 78 degrees. Not stable at all. However, aryl diazoniums, what you would take from taking an aromatic amine like aniline, is aniline more or less basic than an aliphatic amine?
Less basic.
Yes, it is less basic. The low rate of electrons and the nitrogen are tied up in resonance, and so they're not going to be as nucleophilic or basic. So if you take aniline and do the Hono conditions, you will get an aryl diazonium. Do this whole mechanistic stuff here. And so aryl diazoniums are a little bit more stable than their sp3 counterparts. Whereas these are not stable at minus 78 degrees. Aryl diazoniums are isotopal at minus 40 degrees. So we can at least see this spectroscopically, we know it exists at minus 40 degrees. So they're not necessarily stable, but we can get them in a typical organic lab setting and then do chemistry with them. So these are still fairly much reactive intermediates. But a couple of cool things you can do with them. Since they're so unreactive, you can pretty much turn your diazonium into anything you want, as long as you have the appropriate copper reagent. For example, if you have copper oxide and water, two-way mechanism I won't go over, so don't worry about it. But if you have copper oxide and water with your aryl diazonium, the product you will get out will be a phenol. And this is cool because this is the only way I've ever shown you how to make a phenol in this class, right? So now you know how to make phenols. Conversely, if you have a copper halide, so copper bromide or copper chloride, the product you'll get out will be replacing the diazonium with their halide. Where X equals Cl, Br, or F. So, is this route to make an aryl halide better or worse than aromatic substitution?
Quicker.
Better or worse? Well, it's got its pluses and minuses. The big thing here is, in this route to make an aryl halide, we have to worry about redoselectivity. Absolutely not, right? Because the halide's going to go where the nitrogen was initially. So if you want to have a complete and utter control over your your regio selectivity to make an aryl chloride or aryl bromide or aryl iodide, this is the way to go because it's going to be direct. Where your nitrogen was in the aniline is where your halide is going to be in the product. So, you know, it might not be as easy to run, and it might give you a very unstable, possibly expensive intermediate. It will give you complete regio selectivity, and that's nothing to shake your hand at. Staying on with the copper trend. What product will we get out if you use copper cyanide? If you use copper cyanide, what product will we get out?
Aryl nitrile.
Nice, the aryl nitrile. So for all intents and purposes, if you can get what you want to add on your aryl group on the copper, you'll be able to get it on your aryl group through this diazonium-based chemistry. Yeah.
Could this work if there was like, say, some other group, para to
Yeah.
the diazonium?
Yeah, no, and that's the great thing about this chemistry, is it doesn't matter what groups you have in your aromatic system, your regio selectivity and your regio selectivity and your reactivity are going to be determined by this, not your electrophilic aromatic substitution properties. And so everything we learned in chapter 16, which 15, which is still good stuff to know, if you want a product that you can't get through that way, this is the way to go if you can get the iron. And you know, like I said, students in my lab have ran this several times in the last year. Even though we're an electrophilic aromatic substitution lab, who are really good at it, I don't want to brag, but we're probably the best in San Diego. We will use this chemistry to make things we can't make with our chemistry because you get such good regio selectivity. In essence, the way you can think about it is, with this strategy, your regio selectivity is pre-programmed into your starting chip. Whereas with electrophilic aromatic substitution, you're at the mercy of the inherent selectivity of the molecule, so the molecule wants to go ortho or para. Whereas in this case, it don't care if it's ortho or para, all it cares is where the amine is. So the regio selectivity is pre-programmed in your aniline, and then it'll be transferred all the way through the synthesis to put your X group here through this chemistry. That's useful. Just one more application. So, another thing people like to do is like to throw in phosphoric acid. And if you throw in phosphoric acid, you're going to replace the diazonium with a hydrogen. So this is useful if you had to have a nitrogen to direct an electrophilic aromatic substitution, let's say, and then you've got your product with the nitrogen and you want to get rid of it, you can just say, oh, let's use diazonium chemistry and get rid of it. So, you know, that's a good way to make a nitrogen a traceless directing group. So that's good stuff to know right there. Again, it's not mechanistic at all. They think the copper chemistry goes through a radical mechanism, but it's not necessarily, at least to me, it doesn't seem like it's a very well-defined radical mechanism, so I don't want to touch that with a 10-foot pole. But it pretty much is thought that this nitrogen-carbon bond just homolytically breaks apart to give you a nitrogen radical, and then give you a nitrogen gas radical, and then to give you a aryl radical, which quickly globs onto the copper. But don't worry about that. Yes?
For the halide, can you use iodine as well?
For iodine, good point. So iodine so reacts. Iodine, you don't need to use copper iodine. You can just use I minus. So I guess I'll write in parentheses, you want to do iodine? You can just use potassium iodide or sodium iodide. for reasons I really couldn't explain well. So that's one nice thing, is being able to do these copper substitutions to replace anilines, reveal selectively, pretty much anything we can think of. The other good thing about emerald diazoniums is the colors. So, turns out that this nitrogen in the aryl diazonium is actually pretty electrophilic. I'll just draw the resonance structure. So we can imagine this bond going over to here, making this nitrogen neutral. But since this nitrogen lost this bond, it lost some electrons, so it will be a positive charge. So based on this resonance structure, there's a bit of positive charge of this nitrogen. And we can almost think of this as almost like a pseudo-carbonyl carbon. And so what that means is diazoniums, specifically at the nitrogen, are actually good electrophiles for the electrophilic aromatic substitution. Meaning, if you take an electron-rich aryl group, and let's just go with methoxybenzene or anisole, it will do an electrophilic aromatic substitution. Do you think it will prefer ortho or para? As always, it will favor para over ortho. Although my lab is some of the first chemistry, we now have a catalyst that favors ortho over para, and it's really awesome because there's no literature precedence for a catalyst that favors ortho over para electrophilic aromatic substitution, so we're pretty excited about it. It's always cool when you're the first person to do something. Is Sean here? No, he's not. My graduate student killed the project. So anyway, though, we will do an ortho electrophilic aromatic substitution at this nitrogen. That will give us these compounds here. So we call these guys, well, they're diaza compounds. More specifically, they're diaza dyes. So this electrophilic aromatic substitution of electron-rich aryl group onto the nitrogen, the distal nitrogen in the diazonium will give us these compounds, and they have crazy colors. Odds are there's a fair amount of these chemicals in this room right now just on our clothes. So these are common, really linchpin molecules in the dye industry. And depending on whether or not you have an electron-rich or an electron-poor aryl group here, it will decide which color it is. So that's kind of cool. Nice dyes, and so they make a lot of dyes through this diazonium chemistry. And obviously these diazoniums are quite stable. These products are quite stable because they're on our clothes, so they have to be stable. Or else they wouldn't be very good dyes. But there's another really cool thing about these molecules. So I drew this in the trans conformation. But it could also exist in the cis conformation. So which one do you think it favors, cis or trans? It turns out it depends on what wavelength of light it's in. The cis and trans isomerism, which one we get, is completely dependent on the wavelength of light. So what wavelength will give you cis, and another wavelength will give you trans. I forget the numbers. I think it's like 450 and 300. But don't quote me on it, but just to make it look good, I'll write those numbers. And don't worry about the light, what the actual wavelength is. Just realize the wavelength of light that it's being exposed to will determine if it's cis or trans. So why is this cool in the last 3 or 4 minutes? That's some cool control, right? That the entire time we're telling you it's all thermodynamics, trans is more stable, which it is. Cis, you can get cis under kinetic conditions, which is true. But now I show you, if you replace 2 carbons with 2 nitrogens, now it's completely determined by the wavelength of light it's in. So that's a cool concept. And it's got a lot of really, really cool applications. I just want to show you an example. And the example I'm going to show you is in general, it's from a field I really like. It's a field called chemical biology. Chemical biology, and I like to think myself as a practitioner of chemical biology, is the field where chemists try to take chemical concepts to ask biological questions. And so what a number of people have done recently is they'll take a drug. And a drug will typically bind the enzyme in a certain way. And let's say it binds in the enzyme. And they put up one of these diazonium compounds off of it. And let's say it turns out, and a lot of times this is very true, that only one of the diazonium forms, cis or trans, will bind the enzyme, and the other won't. So most commonly, the trans will bind the enzyme and the cis won't. So you make this drug-like molecule, you make the analog of the diazonium, and now you have one version under one wavelength of light that will bind the target and do its thing, and you have another version and and you have the isomer that's now cis that won't bind under another wavelength of light. Yes?
Is this how to deactivate some drugs that you're using, like for body?
This has only been done in test tubes and animal models. This hasn't been done in humans yet. And so, but you're exactly right. So what happens now, and the example they did was capsaicin. You guys know what capsaicin is? It's the thing that makes food spicy. And so they made a derivative of capsaicin with this diazo compound. And pretty much what happens is, under one wavelength of light, it's spicy. Under another wavelength of light, it's not spicy because now it can't bind its target because it's switched. And so now they have light-sensitive, spicy foods in test tubes for scientific things.